So the domain for the data in column A is apparently Greek letters, as is the domain for column B, and apparently the domain of valid data values for columns C and D is integers. And so if this were our table, if this were the entirety of our data set, and what the user wanted was for us to select all of the rows where the value of A was exactly equal to the value of B, and also the value of D was greater than 5, the way we would write that, and it's written right there, but I'm just going to write it on the board here to, I don't have room on the front board, to give an alternate view of the same thing. This is, we are selecting data, and so you'll remember from class on Friday, I said the selection operation is represented by lowercase sigma in Greek. That's that symbol over there. And then what we do is we put the, what is the technical term? The conditional. I don't think that's the term the book author uses, but we're going to put the condition as a subscript to this symbol. And so basically the value of A is equal to the value of B, and I'm just going to separate with commas, and D is greater than 5. And so we're selecting according to these details from the table R. So that's how we're going to represent it mathematically. It's further away from human language. It's symbolic representation. It's not true math, but we're just representing what we want from the system. And eventually, this is sort of like a middle language that actually gets translated into a numeric language that your database understands. But we're trying to take something that's kind of complex and reduce it to its essence, reduce it to as simple a representation as we can. And so that's what they came up with lowercase sigma. Out of R, grab all data where A values are equal to B values and D values are greater than 5. And so if I look at these values that I ended up with, these values did all come out of this table that I selected them from. And what I see is this data fits those requirements that I demanded. Both of these values are the value alpha. And so the value of A is equal to the value of B. And then the value of D is greater than 5. Same thing down here, both beta, beta, and D is 10, which is greater than 5. That also came from the data set. And these other rows where the values didn't match, there A was equal to B, but this is an AND, so both of these things have to be true. This value is not greater than 5. That row did not get selected. Same thing here. That row, that value is greater than 5, but these values are not the same, so that row didn't get selected. Only selected these two rows. Predicate, that is the term I was looking for. Predicate is just a fancy term for the conditions that you need to satisfy. So, a selection operation, generally, well, it says it works on a single relation R, but that single relation R can be a combination of tables already. It can be the virtual table that's created through the joining of table 1 and 2 and 3 together into a massive super table. And so, but the way this operation is generally represented, or the parameters that this operation needs, is it's going to run on a table, and it's going to have a list of conditions that it needs to satisfy. And they define the rows that get retrieved or selected from that table. Again, we use this symbol because it's the lowercase sigma character, which is Greek, so that's our alphabet, and that's the symbol for selection. Does this make sense? Later I can show you a sigma expression, just write it on the board and you can tell me what it means, especially if I also give you the design of the table, that is column names and things. Those would be the things that would go inside the predicates. All right. I'm just to give you a different example, because that one came straight from your book. This comes from another book that I didn't ask you to buy, because why pay $200 for two separate books? This is just, another table, but that is used by some real estate company trying to rent houses or sell houses or something like that. And so apparently they've got administrative staff and they want to retrieve out of the staff table. I guess we don't have a name for this, but I guess it's the staff table. We want to retrieve out of the staff table, we want to select all of the rows meeting the qualification salary is greater than 10,000. And I don't think we're seeing the original table, but we can at least verify that all of the rows that were returned to us as a result of submitting this query to the system, all of the salaries that were returned to us have values greater than 10,000. So I'm going to assume there are only 4 staff in the staff table whose salaries were greater than 10,000. That's suddenly, I hope that's like monthly or weekly or something, because that's not much for a yearly salary. All right. So as I illustrate all of these things, I'm going to show you the example from the book, and then I'm going to go to that real estate company and show a result taken from that table. And you'll be able to tell just from the color scheme which book I'm talking about. But okay. Selection of columns. Okay. Right now we're going to talk about projection, which uses the Greek letter capital Pi. And the meaning of projection actually is selecting columns rather than rows. So we've just talked about sigma for selection. Now we're going to talk about capital Pi. We have a symbol for capital Pi here from the book. Also, if you're using it in Microsoft Word, it might come out just looking like a square corridor or something. Square opening. So we've got this relation R. It's got three columns, A, B, and C. It has some data inside it, some Greek letter domain and a couple of integer domains. And what we want to do is we want to grab columns A and C. We don't need to see column B. Column B is maybe some sort of ID that makes no sense to us. We want to see actor names and movie names. We don't care about the auto number ID or whatever this is in column B. So this is the projection operation. We are selecting only the columns of information that we want out of a table. And this works pretty much exactly like selection does. If this were a function in a programming language, the only parameter it would require is the name of the table that we are selecting the columns out of. And so what that looks like is capital Pi, and then we're still going to have that predicate. We're still going to have the values of the columns that we want to get out there. And so, again, you all have a monitor nearby that shows you what this looks like, but I'll just do it again on the board, the handwriting version. It's just capital Pi, and as you see, just the names of the columns are what we put inside that predicate, and the name of the table is inside the parentheses. So we want columns A and column C out of relation R. If this is relation R, then we want these guys. And what the author is saying here is, at this point, that we're talking about mathematical sets of values, and in terms of mathematical sets, this row is exactly the same as this row. By taking out the values that individuated the rows that were returned, we ended up with two things that are exactly the same. And so in terms of mathematical sets, math is just going to consider both these things to be the same thing. And so essentially this table is essentially the same as this result. It's like you're living in a world with only unique numbers. You're not going to find 2 17s in your bag of integers. And so this is just a technical detail, because your database uses the math in order to do the evaluation, but it doesn't actually follow the math when it gives you your result. Microsoft Access will give you duplicate columns because the result that it generates out of tables, it doesn't consider to be a mathematical set. But the author is getting a little detailed here when he says, okay, well, you know what, in terms of sets, alpha 1 is basically the same as alpha 1. We're only going to return unique values in our mathematical set. It eliminates duplicates in the values returned. And so not only is it returning columns, it returns all the values in those columns. And then if we're being truly accurate about things in math world, duplicates would be eliminated. I don't think it's a huge thing to insist on myself personally, because in the real world, the database isn't going to be doing that. So I'll tell you why the author is mentioning it, and then I'll never do it again. I'll never worry about it again. So if the human working with the real estate database wanted to produce a list of the salaries of all staff, but all they wanted to show were the staff IDs, the staff numbers, the staff names. What's F name? I guess first name, and what's I name? This is a British book, by the way. So, what do the Brits call last names? Oh, maybe that's L name. That's L name. Okay, F name and L name, first name and last name, and salary. And they're retrieving all of that from the staff table. So again, this PowerPoint series is different from my PowerPoint series in that my PowerPoint series showed you the original table and then the result. This PowerPoint does not show me the original table this came out of, which makes me a little bit sad. But we can see that the table that it returned contains only the staff number column, the first name, the last name, and the salary column. And so presumably this table had more columns than that before they were all filtered out. That's what I consider the projection operation to be, is more of a column filter, really. You're just, again, it's like when you're looking at your movies and actors database, you don't really care about the glue stuff. You don't really care about the IDs of movies and the IDs of actors. What you care about are their names and the names of movies. Those are the things that make sense to you. And so you want to filter out the nonsense columns that do make the system work, but you don't care about seeing the underpinnings. You want to see the results. And that's why we use projection in nearly everything we do. We're selecting exactly which columns we care about. These are the values we want to see. And this is often like one of the last things that gets applied to your table. You're first going to put tables together, join rows to rows, and then once you have all of the data together in one table, then you're going to filter out all of the columns that you don't actually care about from the massive table that got joined together. Any questions on this? This makes sense? The second of the 5 basic, fundamental relational algebra operations. All right, union. For union, you've probably actually talked about union in your intermediate algebra and your high school algebra courses. You've got 2 sets of values, 2 tables, R and S. So unioning 2 tables together, R and S, is basically creating a new table, defines a relation that contains all the tuples of both R and S. And if there are any duplicate tuples, then they are eliminated because math, set theory. Do we have a term for what's going on here? I think we have a term for this that we use in CS1 and CS2 already. what were you going to say?
I don't know about CS1, CS2,
Yeah,
but
go
I
ahead.
assumed it would be like a join.
Yeah, it's not going to be a join because that's a non-fundamental thing that we're going to see later. But actually, what is a join? If you were to describe a join to me, I've tried to describe it with my failing vocabulary in the past, but how would you describe join to me?
Um,
I've got table A and table B. How are they being joined?
it's just addition then, in that sense.
What
But kind of you're filtering out.
they're being joined horizontally, right? Concatenated horizontally. That's how joins work, right? I've got the movie table here, I've got the actor table here, and I want the actors to show up on the same line as the movies, and so rows are being joined onto the end of other rows from different tables, and so we've got horizontal concatenation happening. In joins, I'm not talking about join here, I'm talking about union. And it's saying, I take these two tables, R and S, and it ends up giving me a new table that contains all of the rows from both R and S. I don't think this is a horizontal concatenation happening. This is vertical concatenation. And so when it says R and S must be union compatible, what it is saying is if you're going to join two tables vertically like this, they had better have the same number of columns, and those columns had better have the same domains. You're not going to be able to join a integer column to a Greek letter column, for example, right? So union is a little is a little rarer just because it has more constraints on it. You're not going to be able to union two tables together unless they have basically pretty much the same exact design. Same number of columns and same data types in those columns, in the same order and everything.
Okay.
But we're going to see an example of that here. So I've worked my way through the first paragraph here. What does the second one say? If table R and table S have I, that's a variable, a number of integers I, and a number of rows I. So table R has I rows in it. Table S has J rows in it. Then the union that is obtained by concatenating them vertically into one new table is going to have a maximum of I plus J rows. Does that make sense? And why are they saying maximum? Because of mathematical set theory, some of them might be deleted if they end up being tuples. If you end up having two rows that are indistinguishable from each other, because you filtered out the primary key that would have individuated them. So you would expect that if you were concatenating two tables together, one table has I rows in it, the other table has J rows in it, you would say, oh, well, the resulting table probably has I plus J rows. That only makes sense. They're concatenated. But also, set theory would say, yeah, but if there are any rows that are exactly the same as each other, the duplicates are removed, and so that's why you're only going to get a maximum I plus J, but it is conceivable that you have less than I plus J tuples in that resulting table. Again, details. All right, so let's look at relations R and S. Now, R has table names A and B, and names actually don't count here. We don't care that the names are the same. The names do not have to be the same. What has to be the same is the domain, that is the values that can be in that column. So apparently, column A in R is a Greek letter column, and that's lucky because column A in S is also a Greek letter column. So they have the same domains. Also, the same goes with the column B's, an integer column and an integer columm. And so for that, from that aspect, these tables are union compatible, but also these tables have the same number of rows and the domains are in the same order. It's column of Greek letters followed by column of integers. And so all of those together make those two tables union compatible. I can join table B onto the bottom of table A here, or table S onto the bottom of table R, right? Again, I'm probably over-explaining this, right? This feels probably pretty obvious to you. And this would even work if this were column C and column D. Again, the names of the columns don't matter. All Access is going to look at is, are you joining an integer column to an integer column? Because it's not going to join an integer column to a string column, right? Different domains. So the union of R and S is going to be, I had 3 rows and 2 rows, but it looks like we would have ended up with a duplicate row, and the author only printed 1 there for us, because mathematical set theory is very important to this author. Make sense? Union, you've probably heard about that since grade school. We were talking about Venn diagrams, though, probably. So, another way of, when would I ever use a union when I were trying to retrieve data from a database? Well, maybe this, there's 2 tables that have a city column. There's a branches of the real estate company, and a property for rent table in this database. And what we're doing to make these 2 tables union compatible, because they probably got a wildly different set of columns, we are first going to execute projection on both of those tables and only take out the city column. They both got a city column, and now the tables returned by projection are going to be union compatible. It's just going to be one, a single column table, and presumably the strings, right, for cities. And so, and so we can join properties for rent on the bottom of branch. And so list all cities where there is either a branch office or a property for rent. I'm sure that there was, you know, half a dozen or a couple of hundred properties for rent in London, but luckily I don't have to look at London repeated 117 times. And I'm sure there's probably multiple branches of this real estate company in different neighborhoods in London, but we're only seeing one instance of London. This is one example where I like that duplicates are being eliminated. But you know, any city in Britain that has a branch of this real estate company, all those cities are going into this table, and apparently they don't have branches in more than 4 large cities. And every city where they have a listing of a rental property that is available, all of those cities are being added to the list too, and then that list is just being uniquified. So we're only seeing the unique values, and we only end up with a list of all cities where there is either a branch office for this real estate company or a property for rent. There might not even be any branch offices in Bristol, but since they have an apartment for rent there, we end up with Bristol on the list. Again, I kind of wish I had seen the source tables, although the source tables that this data would have come from would be incredibly long. So in this case, maybe I don't care. Questions? Make sense? Happy? You do not look happy, Luke. All right. So yeah, the or, because not all of these cities necessarily have a property for rent or have a branch office, but if they have one or the other, then that city name will appear in this list. All right, what else did I have on that? I stopped writing these things down at some point. I'm pretty sure union wasn't the last thing I did, was it? Selection, projection. Maybe it was union. Maybe union is the 3rd operation I've talked about today. Yeah? Okay. Confirmation. From someone who's listening. Set difference. The difference between 2 sets, we're going to use the minus sign for that. So let's see the definition of this thing before the answer pops up here. We have these 2 source tables, and so we're going to define what R minus S means. This basically creates a table. It's going to represent a table for us, consisting of the tuples that are in R but not in S. So now I can predict what it's going to show. I think it's going to show alpha 1 and beta 1, right? All I have to do is go down the list of R rows and print out the ones that don't actually occur in S. Again, R and S must be union compatible because the data types need to be the same. We need to have the same number of columns in the same order. Again, names don't matter. All right, so is that what I said before? I'm pretty sure that's what I said before. I spoke that row out, I spoke that row out, I didn't speak this row because I saw that there was a copy in there. And even though this guy is unique, we're only printing the rows in the first relation, the first table, that are different from the rows in the second table. So our result would have been different if our expression were S minus R. Then the resulting table would have been beta 3. So order matters in set difference, just like it does in mathematical difference. All right. 4 fundamental operations. I guess there's a 5th. What was the 5th? Feel like I've missed one. Okay. List all the cities where there is a branch office, but no properties for rent. So list all the cities with a branch office. So grab all of the unique city names from the branch table, and then only show the values that are in the branch table, but not in the property for rent table. So I guess that makes sense. If there are no properties for rent in Bristol, but we have a branch in Bristol, it will come in from this table retrieval, and then as we are eliminating all of the copies from those two tables, if there are no Bristol properties for rent, Bristol will not be eliminated from that original list. So I guess that makes sense. That makes sense to you guys? Again, the authors here are trying to show you at least 1 or 2 situations. I kind of like how the reason I'm using examples from this book, even though I don't see source data, is that it's a little bit more real-world situation than my Greek letters and integers made up versions. But at least those guys, the blue and white examples are showing me source tables that, I don't have to work too hard at figuring out what the answer is going to be. But I do like the sort of real-world aspect of this. Here, it tells us, it kind of gives us at least one example where being able to take a set difference would be useful to us in a real-world situation. Okay, yeah, I was kind of wondering why intersection didn't follow union, because I remember in grade school math class, right after talking about union, we talked about intersection. We were using Venn diagrams, and so intersection was where they overlapped in the middle there. All right, intersection defines a table containing all of the rows that are in both R and S. Again, R and S need to be union compatible, same domains, same number of columns, same orders, and yeah, I think what they're saying is intersection is not a fundamental operation, because it's actually built out of a couple of set differences. R union S is equivalent to R minus all of the values in R that aren't in S. Take those values out of R. Does that make sense? If I were to draw up a quick example of that here, Venn diagram style, if I've got this circle, and I have a triangle, and a square, and a circle, and a star, and a crescent moon, and a plus sign. and this is table R, and this is table S. We know that intersection of R and S should return the value crescent moon and star, but I just want to make sure that author isn't lying to me here. And so I want to evaluate this expression, and according to the rules of math, I need to start inside the parentheses and work my way out. So first, let me figure out what set difference of R minus S is. So if I'm going to do this, I better use a working marker. So R minus S is going to be everything that's in R, but not in S. So that's going to be triangle and plus sign, right? It's going to be that set right there. And I am supposed to take the contents of that set and draw all the values in set R except for the values in that set that I created. And so set R is crescent moon and square and triangle and plus, except I can't draw triangle and plus. The result of this is going to be crescent moon and star. Crescent moon and square. Does that make sense? Author told us that this thing, which we kind of knew what it would do if expressed in terms of a Venn diagram, we know that the intersection of two sets should be the things that are in both of those sets. And I just couldn't picture what R minus S would be. But it turns out that it does exactly what we would expect intersection to return for us. It returns only those values that are in common between R and S only by using set difference. And that's probably the cheapest, least troublesome, least expensive way of getting those values is just using two set differences, one after the other, one embedded within the other. This actually gives an easy way to explain to a computer, if we're writing a program, how to generate a list of all items in common between two sets of two sets of containers, two lists, two vectors. Just a couple of for loops, really. Do it. All right, so let's confirm that that we understand what this is doing. I've got these two sets. They are union compatible, and I want to figure out between relations R and S what the intersection of R and S is. That is, what are all of the rows that are in common between these two tables. I think we can just see from this example that it's going to be alpha 2, right? Am I interpreting that correctly? And so if I click this, the author shows me alpha 2 is the only item that's in common between these two. And I could have done that R minus S thing and come up with the same answer. That's probably how it's implemented in my computer. And so we're going to assume that it's correctly implemented on this British real estate computer, and we are listing all of those cities where there's both a branch office and at least one property for rent. And so since we knew that there were 4 cities at first that were combining the cities with branches and properties for rent, and we saw that there was what was that last query? No. A city with a branch office in it that had no apartments for rent, that was Bristol. And so apparently that means that Aberdeen, London, Glasgow, and Bristol are branch offices. But since Bristol had no properties for rent, then the only union between branch office cities and property for rent cities is going to be these 3 locations here. But other than this, when am I ever going to feel a need to use intersection in the rest of my life? Right? Intersection. And is the important logical operator in intersection, I guess. Okay, I feel like Which is the fundamental operation that I forgot to write down on the board? No, it's selection, projection, and did I only have 4? I feel like there were 5 on that list. Now I'm just wasting you guys' time. I'm checking there it is. Oh, it's because I haven't illustrated Cartesian product, that's why. So you can see that I've illustrated selection, projection, union, and then we showed you intersection after we knew what set difference did. We know that we can build intersection just by embedding a set difference operation inside another set difference operation. Okay, now my confusion is resolved. You know what? You know why I bet I removed Cartesian product from this is it's kind of a long example to try to fit into the last 6 minutes of class. But hey, I'm gonna try. Hey, here we go. Cartesian product. Time for me to erase stuff and make room. I don't have intersection here. I'll just throw intersection down here at the bottom, but it's not one of the fundamentals. But apparently, set difference is, we're just going to use a big multiplication cross for that. All right, so R cross S, our Cartesian product S, is going to define a new table that is a concatenation, and what the author means is a horizontal concatenation, as we've established already, of every tuple, every row in table R, combined with every row in table S. Now, I want you to realize that the join statements that you built for me in homework 1 were not every row with every row in one table with every row in another table. They were only rows where the values matched in a particular field, right? That's why we drag and dropped from one table schema to another table schema. We were selecting the field where the matching fields where the values had to be the same, or the corresponding fields that had to have matching values. This is different. This is connecting every row with every other row in both those tables. That's why I underlined the every in that description. So, if we are Cartesian producting table R with table S here, we are going to end up with 8 rows. We have 2 rows in one, we have 4 rows in the other, and what we're going to do is horizontally concatenate alpha 1 with those 4 rows, and so we'll end up with a table with 5 columns in it, and then we're going to add another 4 rows where those 4 rows all start with beta 2. Right? Horizontal concatenation, every row in one table gets horizontally concatenated to every row in the other table. R cross S looks like this. Am I right? Did I describe that accurately? You see what happened there? We connected alpha 1 with alpha 10A, alpha 1 with beta 10A, alpha 1 with beta 20B, alpha 1 with, oh God, gamma? Gamma 10B. Who knows their Greek letters? Is that gamma there, Tyler? Okay. I think it's gamma. Then there's another one that I just call squiggle. I don't know if that's if they use it in databases though. That makes sense? Every row with every other row. Horizontal concatenation. Why would we want to do that? It turns out that Cartesian product is the most computation intensive operation in logical, in relational algebra, but it is required in order to do those joins that you did in homework 1. First, in order to end up with that more limited set of these rows are matched because of matching values, first we have to go through this to determine if there are matching values in the rows that we care about. So we're not doing join now. This is just the first step in a join. And it's basically, showing every possibility of rows joined with rows. These two tables are ridiculously tiny, right? The tables that you have in your actual databases probably have 1,000 rows each in those tables. And so doing a join between two tables with 1,000 rows each, that's like 1,000 times 1,000, 6 zeros, 1 million rows. This is super expensive. So, what's going on here? We're listing all combinations of the names and comments of all clients in our database. Our clients are in a client table, and these are clients who have viewed properties for rent, and so after viewing a property, the real estate agent asks them to write down their comments, whether they're interested in the place or not. That gets placed in the viewing table database. I can see that because we extracted that comment field from viewing, and apparently there was no comment field in the client table. So out of the client table, we took the client number, ID, first name and last name, and out of the viewing table, we also took out the client number table. And so the names are the same. That doesn't necessarily mean that the data is the same, the domain is the same, that the meaning is the same. But in this case, probably, it's probably client ID in both of those is the meaning. And so there's also an ID for the property number, and then the comment for that particular property. And so what do we see at the adjoined table for this? It has 1, 2, 3, 4, 5, 6 columns. Yes, we have the client number from the client table. First name and last name, they're not prepending the name of the table to that because we know that only came from one table. But we have client number from the viewing table, and so we're showing both of those. And those numbers aren't the same. They don't need to be because every row in the client number table was joined to every row in the viewing table. And apparently, it looks like it was joined together the same way that the previous table worked. Is we just joined this guy to everybody, and then we joined this guy to everybody. And so what I'm seeing here is that the client table apparently only had client CR76, CR56, CR74, and CR62. It looks like the client table only had 4 rows in it, which is necessary if we only want a Cartesian joined table of 40 rows or so. Not even 40, something like 5, I guess. There were 5 rows in the other table. The other table had the clients who left comments. Some clients didn't leave comments, I guess. But CR 56, 76, 56, 62. It's hard for me to figure out how many rows are in the viewing table from this. I guess there are only 1, 2, 3 unique values here. 3 times 5, 15. Do we have 15 rows here? We seem to have about 20 rows here. So maybe I'm missing a unique value. CR 56, 76, 62, and I'm only seeing 3. Anyway, clearly these 3 columns came from the viewing table, and these 3 columns came from the client table. And every column in the client table was eventually joined to every column in the viewing table. I guess these are all 5, so is it CR 56, 76? Oh, because 56 saw 2 properties. That's why he's in there several times. Customer 56, CR 56 saw 4 properties. And he didn't leave, 3. 1, 2, 3. He left, he didn't have any comments on this one or that one, but he apparently thought that one was too small. Okay, so it looks like there were only 5 rows in the viewing table that got matched up to each row in the client table. Does that make sense to you guys? Again, we can tell that these are the same rows every time because they repeat every 5 rows. Too small, too remote, blank, no dining room, blank. Too small, too remote, blank, no dining room, blank. And so yeah, These 5 rows are being joined with these 4 rows. So I guess that must mean that this is a table with 20 rows in it. That's Cartesian products. Makes sense? I mean, you don't have to like it. It's not a very efficient operation, but it is going to help us get done what we need to get done eventually when we get around to joints. All right, so I have overrun my time with you. Thank you for showing up. I will see you back here on Wednesday. Also, just so you guys know, I am going to start canceling classes here in October because my wife is having a surgery, so I'm going to be out of town for the last half of a week, and then the following Monday is going to be a day off. So we're going to end up missing an entire week of database classes. Wednesday, Friday, and then the following Monday. To everybody's chagrin, I'm sure. Mr. Kapisky over there really wishes that he would get his full money's worth out of this class, but not this semester, buddy. All right, but I'll tell you more about that later. It's going to be around October 8th or so. All that happens. Pardon? And there are no classes this Friday. That's correct.
No classes this Friday.
But that's not my fault. That's the administration that canceled.
Can I show up anyways?
Yeah, yes, you can.